It is unnecessary to bring your bike into a bike shop just because the shifting is not working correctly. The usual culprit is loose cables. The gear ratios that your bike is capable of delivering to you are necessary to allow you to ride through a variety of terrain. There is actually an optimum speed at which you should be pedaling. Ideally, you should be pedaling at between 60 and 90 pedal strokes per minute. By doing that, you increase the biomechanical efficiency of your body. It is far easier to pedal at a higher cadence with less effort per stroke. You will find that you will go further and you will save your energy. By shifting your gears into a lower gear, making it easier to pedal, it allows you to sustain that optimum pedal stroke at optimum cadence. You know when to shift when the effort requires you to actually slow down your pedal stroke to a grind. When you can no longer turn your pedals over at over 60 RPM, it is time to shift to an easier gear. So, as you approach a hill and as you start to feel the resistance on the pedal stroke, shift into an easier gear so that you can maintain that optimum RPM. When you start to ride down a hill, shift into a higher gear that will allow you to go faster and maintain that higher cadence as you are pedaling downhill with less resistance. So, make use of all your gears and you will be able to ride further and faster, and you will be able to keep up with faster and more experienced riders. The gears are there for a reason. It is important that you are able to shift into all those possible combinations so that you can make the most of biomechanical efficiency out of your engine, and your engine is you.
We've been down to the workshop, we've looked at the very complicated mechanism that is a car gearbox. And it is very complicated. What I want to do now is just spend a few minutes trying to explain some of the basic principles of gears and use something which is not as complicated as the car gearbox. You may say, why do we need a gearbox in a car? Why can't you just connect the wheels directly to the engine? Because you can make the engine go slow or fast, so you could make the car go slow or fast just using the accelerator. Why do we need a gearbox? And in order to answer that question, we have to think about this. The normal lowest speed of a motor car engine to be effective is about 1,000 revolutions per minute. Now, if I were to connect the wheels directly to the engine, it would mean the back wheels were going around at 1,000 revolutions a minute. And for the average motor car, this would mean it was going at about 75 miles an hour. So, if you didn't have gears, but it was direct connection between engine and back wheels, as soon as you turned on the engine, no touching the accelerator, the car would zoom off at 75 miles an hour. And in fact, if you were to increase the rotation of the engine to about 6,000 revolutions per minute, you'd find your car would be going at about 500 miles an hour. Obviously not practical. We have to have a way of reducing the engine speed so that when it drives the back wheels, they're going at a rather slower rate. And that is the function of the gearbox. What I'd like to explain is that fundamentally, gear systems can do three things. First of all, they can change the speed of movement. And I just mentioned that in a motor car, the gears are used to turn the fast revolutions of the engine into a slower revolution of the back wheels. So gears can change speed of movement. The second thing that gears can do is change force. So I can magnify a force. And this happens in motor cars as well. when I can magnify the force of the engine in order to make the car accelerate. The third thing that gears can do is change direction of movement. We see this in a motor car gearbox, where by changing the connections of the gear wheels, I can make the car go backwards or forwards. So, functions of gears: changing speed of movement, changing the force exerted, and third, changing direction. So, I've got a large wheel here, and with a little switch, I can make it go round. And then I have a series of different sized wheels. Let's turn this round. I wonder if you can see the black mark there. And I've made a black mark on this wheel. Let's put them together. Let's make the big one go round once and see what the smaller one does. Will it do one revolution, more than one revolution, or less than one revolution? Watch the black marks. So, there's the black mark again. The small wheel has gone round one revolution plus a quarter of a revolution. So the small wheel has gone round faster. And this happens wherever you have a big wheel connected to a smaller wheel. The smaller wheel goes round faster. So here we have an example of a gear being used to change the speed of movement. The big wheel is going round like that. The small wheel is going round more quickly. And if I take that away and put an even smaller one there, one, two and a bit revolutions of the little one compared with one revolution of the big one. So here the gears are being used to change speed. And of course, I can put gears in a train like that. This is going that way, the middle one is going backwards, the third one is going that way again. Fundamentally, whenever I connect two gear wheels together, if one goes clockwise, the other one will go anti-clockwise. Now, I've changed the direction of movement, and this is how we can get reverse gear in a motor car, because this is going round that way at the moment, but if I just disconnect there and put that instead, now the green wheel is going clockwise. If I take this out and directly connect them, the green wheel is going anti-clockwise. So here is how I can use gears to cause change of movement. That way, that way. You notice this, that, and that. What happens if I put another one in here? Which way will this go round? Well, clearly, if I connect this in, it's going that way. So it's very important to be able to work out which way a gear wheel is going to go in a train of gear wheels. But you notice if I put that in here, this wheel will make it go that way and that one will make it go that way. So it all works. So we have this purple wheel being driven by this wheel and that one. And of course, I can make things go much faster. Small wheel is going about twice as fast as the big one, and the little ones with another gear inside, they're going round much faster. So, point number one, gears can be used to change speed of motion. Point number two, gears can be used to change the direction of motion. And we saw in the motor car workshop a very interesting example of gears being used to change the direction of motion when we looked at the car differential. The drive from the engine comes down the propeller shaft into the differential, which then turns the road wheels. So we're turning that movement into that movement. The motion is changing its direction through 90 degrees, that way to that way. So gears, I repeat, can be used to change direction of motion. They can be used to change the speed of motion, but they can also be used to change force. If I connect this big wheel to the little one, the little one is going quicker, but there is not as much force from this little one as I get from the big one alone. The force here is reduced compared with the force of the big wheel. So I've increased the speed, but I've reduced the force. And a gear can be used to increase force, but then the speed goes down, or it can be used to increase speed, but then the force goes down. If I can just reverse the situation now, let me rotate the blue wheel. The orange wheel goes round more slowly, but with a bigger force. I'm reducing the speed because I'm going from small wheel to big wheel. If I reduce the speed, I'm increasing the force. We see this very clearly in a moment when we look at bicycle gears. So now I want to talk about bicycle gears. And I'd like to tell you that I've come up here on the way to Buddha Point. In fact, I came up in my car, of course, but I'm standing here because I want to talk about bicycle gears. And I'm hoping we'll get a cyclist coming up here who I can stop and ask if we can look at their bicycle. So let's see if we are. Here comes a cyclist. Now, one important thing which I really want to emphasize, you notice he is wearing a crash helmet. And may we just stop you a moment? I'm sorry to hold you up on your bicycle ride. He's wearing a crash helmet. It is really important because if you fall off your bike and hit your head on the road, you could end up for the rest of your life in hospital as a vegetable. Hit your head on a hard road like this or a rock and you can get brain damage very easily. Always wear a cycling helmet. Sorry about that. I'm pleased to see you've got one on. May we use your bicycle to have a look at the gears? If you wouldn't mind putting your bicycle on the ground upside down here. Whoops. That'd be very kind. Thank you very. I shan't be a minute. Now, here's a bicycle gear wheel. It's large. Instead of the gears being directly connected like that, they're connected by means of a chain. And the invention of the chain was a very great invention. Without it, you'd have to have a whole lot of gear wheels going along here through to the back wheel. A big gear wheel, like this one here. And the chain connects it to a small gear wheel here. And I wonder if the camera can home in so that we can see the small gear wheel there. And you'll notice on the back there are 1, 2, 3, 4, 5, 6, 7 different sized gear wheels. So we have the big wheel going to a small wheel. Just like this, the big gear wheel connected to a small gear wheel, but it's connected by a chain. I'm going to demonstrate this by making it a direct connection. Now, you will notice that if I rotate the big wheel, the small wheel goes round faster. So when I turn this, if you look, compare how fast I'm turning with the pedals with how fast the back wheel is going. And you will see, if I do one revolution of this wheel, 1, 2, 3, 4, 5, this is going around about 6 times quicker. Big wheel, small wheel gives me an increase in speed. So I can turn the pedals slowly, but the wheel goes round quickly. I'm getting an increase in speed. But if we remember the law of conservation of energy, if I increase the speed, I decrease the force that I get. I can't get an increase in speed and an increase in force at the same time. More speed, less force. If I want more force, I have less speed. This is the sort of gear you'd use if you were going a little bit downhill and you wanted to cycle really fast. Now, if I could ask the owner of the cycle to come and use the brake to stop the wheel. Can we stop it? Thank you. Now, can you arrange to change gear here? You can see I've got 7 wheels here. Instead of the chain going around the smallest one, let's make it go around the biggest one. Can we change the gear? Keep going. Up to the biggest. Right, stop the wheel. Now, thanks to the gear changing mechanism on the bike, the chain is now around the biggest wheel. So what we've done is take the big wheel and we've connected a much larger wheel to it. Now, when I turn the pedal, the orange gear goes round a bit quicker, but not as quick as with the small wheel. I don't know whether you can see that. The small wheel goes round quicker than the bigger one. Now we're on the bigger one here. If I now turn the pedals, you will see that the wheel is not going as fast as it was. And if I want to go very, very fast, I have to turn these very, very quickly, which isn't very good, you know. Imagine cycling downhill with your feet going round at an incredible speed, wouldn't be very good. So, what do we use this gear for? Well, we're getting less speed, so we can get more force. Less speed, more force. So this is the sort of gear we use if we're cycling up a steep hill. And we can get even more force because here I can move the chain onto a smaller wheel so that I'm actually getting, I can't show it with this, so that, can we change gear onto a smaller wheel? So this would be for going uphill, but if it's a really steep hill, I can move the chain onto the smallest gear wheel here. Now, if you notice, I'm moving the pedals very fast, but the back wheel isn't going round very fast at all. In fact, it's almost 1-to-1. So this, far less speed, but it will give me far more force. What we mean by that is the force that I press down on the pedal with is bigger here than it was before. So more force, but less speed. The lowest gear for going up the steepest hills. So the use of gears on bicycles is marvellous. A car typically has 5 gears to go forward, or sometimes 4. This has got 1, 2, 3 and 7, 21 gears. Multiply the number of gear wheels here by the number of gear wheels there, and that's the total number of gears. 3 times 7, 21 different gears. Now, if the cyclist would mind coming up here in this gear, pedaling very fast, but not travelling very fast, but lots of force, you can get up a very steep hill, and then do the same thing, come up towards us in the lowest gear, not pedaling so fast, but having to push much harder because I'm not getting the force magnification. And we can see the incredibly useful function that gears carry out on a bicycle. In fact, on a mountain bike, in a country like Bhutan, lots and lots of hills, in the gear I'm in now, my little bicycle here, for going up steep hills, has just got 1 gear wheel here, 1 gear wheel there. It's got 1 gear. This has 21 gears. So this children's bike is fine for going along the level, but if a child tried to cycle uphill with this, they'd find it very, very hard work. So do you think, would the cyclist, would you take your bicycle and demonstrate for us what it looks like with these gears? Go down the road and come up towards us in the gear I'm in now, which is low gear for going up steep hills. Now, we notice he's in a gear where we get a small wheel at the front and a bigger wheel at the back. Low gear. He's having to turn his feet very rapidly to go quite slowly. So he's getting less speed, but he's getting more force. Now, he's coming downhill, and so he wants lots of speed and not so much force. So this gear is fine for going downhill. The gearing systems anywhere can be used, I repeat, for 3 purposes. Increase the speed of rotation or movement, increase or decrease the force of rotation, and to change the direction of rotation. And we can see that very clearly with these. If I take this and that, big wheel, little wheel, many, many teeth on the wheel, fewer teeth on the wheel, we can see that if I turn the green one, the blue one turns more quickly. Increase in speed, but the force I'll get from the blue wheel will be reduced. If I double the speed of rotation, I will halve the force that I can get from this wheel. So there we have a system where the gear is increasing the speed that I'm rotating the green wheel with, but halving the force of rotation. If, on the other hand, I rotate the blue one so that the small wheel is the driving wheel, the green one goes more slowly, half as fast, but I will get twice as much force from the green wheel. So now I'm using the gear wheel to magnify force. Now, if I can use the gears to magnify force and speed, surely this is marvellous, because I could use the gear wheels to make more energy. But unfortunately, that is not how nature and physics works. You cannot get more energy from this system, because if I magnify the force, I reduce the speed. If I magnify the speed, I reduce the force. I cannot increase the force and the speed at the same time. And if I would manage to do that, that would be against the law of conservation of energy. The law of conservation energy cannot be broken, so I have a choice. More speed, less force; more force, less speed. And we're constantly making that choice when one drives a motor car. When you start off, you need a big force to get the car moving, but it's not going very fast. So you use the gears, what's called low gear, to reduce the speed of the engine a lot so that the back wheels are going slowly, but because they're going slowly, you can get a big force. However, when you're going along a nice straight road and you want to go fast, you want more speed, and because it's a straight road, you need less force. So you can get more speed, less force, or more force, less speed. And the whole art of using the gears when you're driving a car is to tune your gear to the conditions that you're driving in. If you're driving uphill, then you need a low gear to get a lot of force, and you can't go very fast. If you're driving straight and level, then you can use a high gear because you don't need as much force, so you can get more speed. And tuning the gears to your driving circumstances is one of the main and most difficult skills of driving. And it's equally the same with a bicycle. When you start off with a bicycle, you want a low gear because you're not going very fast, but you want a big force. So you want a gear system that will go slowly at the back wheels, but give you a lot of force. But as you go faster, if you were not careful, your feet will be going around so fast they'd fall off. As you go faster, you need less force, but you need more speed of the back wheel. Let's go and look at a bicycle in a moment and see how all the gears on a bike help make riding a bicycle easier, especially in a hilly country like Bhutan. You remember I said earlier on that gears can do three things. They can change speed, they can change force, and they can cause a change in direction. We've seen very well with this bicycle how by changing the gears at the front and the back, I can increase the force that I'm using to accelerate me up the road, up a mountain. I can increase the speed that I make the back wheels go round with if I want to go very fast downhill, not much force, but a lot of speed. And we saw in the car differential that I can change the direction of rotation using my gears. And if we look at this car going up the hill at the back, we remember that at the back, driving the back wheels, there is the differential gear, which causes a change in direction of the force. Gears are therefore very, very useful. We've seen with a bicycle, the gears are very obvious. And we've seen there are 7 gear wheels here, 3 gear wheels there, giving me a total of 7 times 3, which is 21 different gear ratios. And we've seen that if I'm going uphill, I want a lot of force, so I don't get much speed. So I have to pedal very fast to make the back wheel go round even quite slowly, but I get a lot of force. And if I'm going on the flat or downhill, I can change the gears so that I pedal slowly, but the back wheel goes round very fast. I'm getting more speed. And the fundamental lesson of what we've seen about gears is to remember what you've learned in school, the law of conservation of energy. The law of conservation of energy tells us I can't make energy out of nothing. It tells me that if I get more force, I'll get less speed. If I get more speed, I must get less force. It's like a seesaw. More speed, less force. More force, less speed. There's no such thing as a free lunch. I can't get something for nothing. If I want more force, I have to sacrifice speed, and vice versa. So remember, the law of conservation of energy is an essential part of thinking about gears in motor cars, bicycles, and in all sorts of other systems where we have gears. Go around. When you're going around, look for gears all over the place. There's a gear system there. So gears are all over the place. Thank you very much indeed to Cyclist for demonstrating with your splendid bicycle. Much better than the children's bicycle there, which just has one gear. And go carefully and always wear your crash helmet. Thank you.